Hey guys, we are Team 43 presenting our final project 3D reconstruction. Today we'll be discussing about people involved, overview, project setup and the pipeline that we followed, the use case diagram and the sprint backlog, what we did till R1, our objectives in R2, and what all did we achieve in R2. So the people involved are
I'm Sarthak Singhal.
I'm Pulkit Gera
And I'm Amar Mahajan.
and our client is Anil Kumar Upadhyay from Five Finger Solution and our teaching assistant is Prateek Kamble. So, what exactly were we doing in this project? In the given project, we had a number of Intel RealSense 2 cameras. These cameras were recording the scene and were providing us the depth images in real time. Using these images, we would be stitching and wrapping around a panorama, which would be then used to generate the 3D reconstruction. So the setup. The given project required the following setup. For cameras, we had Intel RealSense 2 cameras, and the softwares involved were OpenCV and RealSense 2 libraries. The project pipeline included three steps. Majorly, the first step being the collection of image set. That is, we were collecting images from different setups and finding the optimum set of images from the Intel RealSense 2 cameras to minimize occlusion. The second step being image processing. This was the most important step in our pipeline and involved the finding of homography matrices or essential or fundamental matrices in order to help stitch the images. The final step being wrapping. Once we have stitched the images, we needed to wrap the panorama around in order to get the 360-degree view. Here is a rough use case diagram. As you can see, the actors being client, program, and 3D engine mainly. Also, the plan followed by the team was in line with the Agile Scrum methodology. The sprint backlogs. So basically, we had four major sprints in our entire project. The first being image collection, that, as I mentioned before, was collection of different sets of images from the Intel RealSense 2 cameras. The second step being image formatting, which involved figuring out the essential and the fundamental matrices which would be used in stitching of these images. The third step being using the key point matches and the matrices that we have calculated, we would be stitching these images and figuring out different algorithms in order to reduce the lag. The fourth step being panorama generation. This would be done in real time stitching the outputs and converting the rectilinear panorama into cylindrical panorama. So, what are the goals that we achieved till R1? So in this project, we were given to reconstruct a given scene. We had different obstacles and we learned about image processing and the different sprints were assigned to different members. So in R1, the major pipeline was that we were detecting key point matches using different algorithms and we used SIFT eventually as it being the most efficient. The second step was the most important step being the calculation of homography matrix. This would help us in order to stitch the different images together. The final step being the stitching of different images using homography matrices. As a result of all the efforts, we were able to stitch simple images into a panorama, which were using a same viewpoint. However, this is where the problem started coming. We were There were majorly three problems. One being that we were not able to use depth into account. Since this is a 3D reconstruction, we needed to take the depth into account. Second, multiple viewpoints. Because of different cameras, we were not able to take multiple viewpoints. Also, the panorama that we were getting was rectilinear, which had to be converted into a cylindrical one. These were the major objectives also in our R2, being depth, real-time stitching, and cylindrical panorama. Real-time stitching was important because since it's a video simulation, we needed to find a way so that we could real-time stitch the videos that we were generating. Also, the panorama generation was important since rectilinear panorama will not be able to it's not possible to wrap it around.
So I'll be discussing depth and fundamental matrix. But before that, let us discuss what is epipolar geometry. Often, if an object is kept in the real world and you take two images of the object from two different camera angles, and if you have traveled before taking the image of the object, then the image, the 3D coordinate of the object in the real world does not change, but in the camera coordinates, it changes. So To make that changes, we need epipolar geometry. For example, if x is the object we want to capture, and if we take an image from the left view and from the right view, then the coordinates in this image and this image will be different, but the real world coordinates won't change. To do this, we need fundamental matrix. So the fundamental matrix encapsulates this intrinsic geometry. It is a 3 by 3 matrix of rank 2. If a point in 3D space is imaged as x in the first view and x dash in the second, then the image satisfies the relation x dash transpose into fundamental matrix into x equals 0. This is very essential for us because we need to warp the image according to the fundamental matrix. To compute the fundamental matrix, we input the key point matches in both the images and use a CV2 library function called find fundamental mat, which gives us the required matrix so we can transform the point of an image into real world coordinates. Extraction of depth. To find depth information, we use a depth image obtained from Intel RealSense camera and use the library function depth to 3D, which gives us the 3D points of each pixel of the image. To find the depth, we must first convert the image obtained from the Intel RealSense camera into a grayscale image. So this is the image that we had obtained from the RealSense camera, and this is the grayscale image, corresponding grayscale image. From this image, we were able to find the depth. Warping the image. After extracting the depth, we apply spatial transformation on the image to warp it. We need parameters such as depth, fundamental matrix, and intrinsic matrix to find the spatial transformation. Once the image is warped, we stitch the images according to the matching coordinates in the real world.
Coming on to our second step, real-time stitching. One of our goals after R1 was to stitch the real images in real time. For multiple simultaneous outputs, we used webcams and phones attached to our systems and tried to emulate. This way, our stitching algorithms were able to run in real time. In order to test out, however, we used the data generated from our phones and webcams. However, in the main code, the Intel RealSense 2 camera will be used. These will be positioned and using essential matrices that we calculated, it will be used to stitch them and presented alongside. The current implementation that we did not involve these cameras, and therefore we were not able to take depth into account, which is why we use the stitching algorithms we use in our till R1. However, once we are able to, since we are able to calculate the essential matrices, we only need to pivot that code and it will be able to work fine along with Intel RealSense cameras as well. And this will be fed in real time. Also, since we have calculated the matrices beforehand and the setup will not change, the computation will not be very expensive and there will not be much lag. Since this code also has CPP bindings, therefore it is also optimized in its implementation as well. So this is one of the this is some sort of an expected output that you can so as you can see, the left and the right frame, both of them have different image inputs and the stitching stitches them well. Our output will be also similar.
Okay, so now we'll study about cylindrical panorama, which was one of our major goals to be accomplished during the R2. So what's this cylindrical panorama? While a classic panorama is taken from one viewpoint by rotating the camera, hence it is often called a 360-degree panorama. Whereas a straight line, linear or rectilinear panorama is basically a multi-viewpoint panorama. A set of photographs is taken from different viewpoints along the street front. So let us understand this with the help of an example. So suppose we want to capture this street and we need to construct a linear panorama and a cylindrical panorama. So a person who wants to construct a linear panorama will move parallel to the buildings by keeping his depth constant from the building and he'll take multiple shots. Whereas a person who wants to construct a cylindrical panorama will stand at one point and rotate his cameras to capture the images. The results obtained by both of them are as follows. So as you can see, the linear panorama captures all the buildings which are equidistant from the camera, whereas in a cylindrical panorama, we see that the points closer to the camera appear larger than the ones which are farther from the camera. So which one to choose now? Though one may consider that linear panorama depicts all the objects clearly, but the main difficulty with linear panorama remains the image editing step. While a classical panorama can be quickly stitched given the right panorama program, a linear panorama needs an elaborate manual editing process. It needs high computation time, our so we chose the classical panorama or the 360-degree panorama. So initially we were getting a linear panorama as we considered only translation with constant depth. But to generate a 3D model, we would need to wrap the panorama, which would be achieved through cylindrical panorama. So now let us look at the results we obtained from cylindrical panorama. So these are the images, 5 images taken from our room. So these images are supplied in left to right order to the program, and the output is as follows. All these images are stitched into a cylindrical panorama. So here we see some more examples of cylindrical panorama. Here in each case about 20 to 25 photographs were clicked by a person who was rotating to cover the 360-degree view around him, and he obtained the following results. So now let us look at the conclusions of our project. So basically we had three main goals after R1 which we needed to accomplish, and they were taking depth into the account, real-time stitching, and generating a cylindrical panorama. Till now, we have worked on these three components individually, which are working fine. However, we haven't been able to integrate these three main components and make them work together, which is where we have fallen short. In the end, we would like to thank our client, Mr. Anil Kumar Upadhyay, the teaching assistants, and the teachers for giving us this wonderful opportunity to work on the project involving computer vision. Thank you.